3. We are going to cover a range of topics today. We're going to start with a review of meta-regression from the traditional meta-analysis standpoint, and then move into some look at an application of a meta-regression for the atorvastatin data set. And then we'll move to some miscellaneous topics that that are important to consider in both traditional meta-regression as well as model-based meta-analysis. And then that'll be a good time for a short break, and then we'll pick up there with the introduction to model-based meta-analysis, and we'll start getting into those topics in the second half of today's class. So if you think back to what we've covered in the last 2 lectures, we started thinking about traditional meta-analysis as either fixed effects, where each study is estimating a common treatment effect, or in a random effects meta-analysis, where each study has its own study-level true effect that it's trying to estimate, and those come from a population distribution. So we have that hierarchical nature of the model. And the effects there of interest are that overall population mean, as well as the between-study variability in the in those treatment effects. With meta-regression, what we try to do is to explain that between-study variability through regression models, and that's what we'll really be focusing on in the next few minutes. And so if you're familiar with just simple linear regression or nonlinear regression, the basic idea of a meta-regression is very similar. We're simply regressing the outcome, which in this case, in a traditional meta-analysis setting, might be a difference from placebo or a log odds ratio, regressing that outcome on a study-level covariates. And the goal there, as I mentioned, was to describe the between-study variability in that treatment effect with those covariates. So you can imagine that it's most likely that a meta-regression will be successful or would be implemented when we're working in that concept of actually having between-study variability in the treatment effect. Of course, sometimes we might be doing our modeling at the treatment arm level, and in that situation, you can it's simple to conceptualize using covariates at the treatment arm level rather than at the study level. But if we're working with randomized studies, particularly if they're large randomized studies, whether we're using those covariate values, which themselves are typically mean covariate values or proportion of subjects in a group, like proportion of males or females. In randomized studies, those should be fairly well balanced across the arms, and particularly in large randomized studies. So whether we use the study level covariates or the treatment arm level covariates wouldn't really matter, because in that part, really, those are describing between study differences. Of course, if we're working with observational data or data from small randomized studies, where we may get differences in the randomized case because of sampling variability, or in an observational setting because subjects may have selected themselves differently, so things like baseline covariates may be different across groups, then we would be more likely to consider using treatment arm level covariates. And what we'll look at in this first part is a very simple classical approach to meta-regression, but in the broader scheme of things, you can really think about model-based meta-analysis as kind of meta-regression on steroids. It's a much more elegant, well, maybe steroids isn't a good example there, but it's a much more sophisticated approach to meta-regression. But is really, I think of model-based meta-analysis is to meta-regression as things like nonlinear mixed effects models are to simple linear regression. And so here's the basic kind of model that would be fit in a meta-regression. So we'll assume, just for simplicity, that we have one covariate labeled as xi, so I for the ith study. And then the general classical fixed effects metaregression model says that our treatment differences, or remember those are theta hat I, is equal to alpha I plus beta times xi plus epsilon I, where epsilon I is our residual, and we assume that has a mean of 0 and a variance of psi squared as before, where that psi is taken to be known, and we'll just take the study level standard error as the standard deviation. So in this model, what we've done is we've replaced what in the previous notation we use as theta here, we've replaced that with alpha plus beta times xi. And this is the regression portion of the model. Whereas before we could just get a simple weighted average of the outcomes to get our estimate. Here we need to be a little bit more sophisticated, and what we find ourselves using is generalized least squares. We're not going to go through the sort of the by hand calculations in this case as we did with the simple meta-analysis case, but in this case now we're going to begin to rely entirely on software to fit the models for us. And we'll come back to how we might interpret these parameters in just a minute. But interpretation here, because we're fitting data using study level data, we're going to need to interpret those as study level effects. The same holds true when we move to a random effects model. The random effects meta-regression model, again, is just a similar kind of extension to the fixed effects meta-analysis model. So again, we have our treatment effect theta hat I. Treatment effect in the ith study is alpha plus beta times xi plus the random effect eta I plus the residual epsilon I. And before, the way that we expressed this whole piece here, alpha plus beta xi plus eta I, we just denoted that as theta I, and we allowed that between study variability in theta I. And now we're allowing the between study variability still through eta, but we're trying to explain some of that between study variability with the beta times xi. So you can imagine that if we are able to explain a good fraction of the between study variability, that tau squared, the variance of the random effects in this case, in the meta-regression model should be smaller than the tau squared from a simple random effects meta-analysis. Because in that case, our tau squared is explaining the residual between study variability in the overall treatment effect. Again, when we're working in the mixed effects or random effects meta-analysis, we're going to move into using likelihood-based methods as opposed to the Dersimonean and Laird estimator. And again, our focus here is on alpha, beta, and tau squared. So one strategy for dealing with heterogeneity is to think about it before you start your meta-analysis and to consider whether or not you'd like to be testing for heterogeneity or to simply assume that it's going to exist. So that would be the notion of whether you'd just be fitting fixed effects meta-analysis models or fitting random effects meta-analysis models. And if you are going to test it, how you're going to approach that. For example, you might use that Cochrane's Q statistic we talked about last time, or you might not choose to test it, but might set up some criteria based on the I-squared statistic. And if you are going to, if you find the heterogeneity, whether you'd like to try to explain it through some study level covariates. Now, typically, all of this is a moot point when we move to model-based meta-analysis, because there we know there will be heterogeneity based on dose or based on time, and the whole purpose of doing the model-based analysis is to explain that heterogeneity. So all of these questions we typically aren't testing it explicitly for any sort of heterogeneity. We're already going into modeling that when we get to model-based meta-analysis. So these are really questions that you're going to be considering more in the traditional meta-analysis setting. So let's think next about meta-regression effects and how we might interpret those. So specifically in this model, how would we interpret this coefficient beta? And we have to keep in mind that we're fitting these models as the covariates themselves are at a study level or at a treatment arm level. The outcomes are at a study level or at a treatment arm level. There are aggregate outcomes that we're working with. And so what we're trying to do is explain that between study, or in some cases between treatment arm variability. And the important thing to keep in mind is that in these meta-regression models, we cannot interpret the covariate effects as patient-level effects. So for example, if xi here was the proportion of subjects in the study that were women, we would not treat beta as being the difference between men being male and female in a particular study. Rather, beta in that context is the difference in the study level treatment averages if we ran a study that was entirely in women versus a study that was entirely in men. And so there's a strong relationship between a meta-analysis or meta-regression and what is historically been called ecological analysis. And ecological analysis in this context isn't an analysis of data from ecology, but it's rather analysis where individuals are defined geographically, they're kind of lumped together, and you might get a cancer rate, for example, in counties in the United States, and then look at covariates for each of those individual counties. So you may look at something like average income in that particular county. So you're working with, similar to meta-analysis, you're working with aggregate types of data. That broad class of models are called ecological analyses. And so there's a large literature about working with those kinds of data and trying to avoid something called ecological bias, which is the difference between the association between of covariates at the individual subject level and at the group levels. And if we make the mistake of making that interpretation, that's sometimes called the ecological fallacy. So we want to be cognizant of that effect when we're interpreting covariate effects from traditional meta-regression as well as from model-based meta-analysis. So here are two examples of ecological bias that have been published. So the first is about suicide rates in 19th century Europe. So someone did an analysis, I can't remember, I guess it was Durkheim, in 1897, looked at suicide rates in countries across Europe and noticed that in countries that were more heavily Protestant, the suicide rates were higher. And his conclusion was therefore that the social conditions of Protestantism promoted suicide. And so based on that, if you were to take an ecological or interpret that at the individual level, you might infer that if you're a Protestant in 19th century Europe, you're more likely to commit suicide than if you were not a Protestant. But that would be the ecological fallacy, because they were trying to interpret that inference about an individual's likelihood of committing suicide based on an analysis that was done at the aggregate level. And the problem is that there are other ways that Protestant countries differed from the primarily Catholic countries other than religion. So the basic idea is that there are confounding effects in that analysis that aren't controlled for. And the difficulty with aggregate level data is that it really becomes almost impossible to completely control for those confounding effects that are happening at the individual level. Another example is the relationship between income and nativity, and this is in the United States. So what's shown here in this figure is data from the 1995 population survey from all 50 states in the United States. What's plotted on the y-axis is the fraction that has a high income. I don't know exactly what the definition of that is, but we'll assume there's some fixed definition of high income. And on the x-axis is the fraction that's born outside the United States. And there was an analysis that was done to show that the relationship between being born outside the United States and having high income was a correlation of about 0.5. So you might infer then that individuals who are born outside the United States are more likely to have a higher income than individuals that are not. But again, that would be falling into this ecological or false interpretation of that association, whereas when you look at the individual level data from the same survey, you see that the individual level correlation is actually very close to 0. And again, the idea here is that there are some confounding factors. In this case, it's probably the fact that individuals who move into the United States are likely to move to parts of the country where there are jobs, and places where there is higher employment is likely to lead to fractions that have higher income. So there's, again, this notion of confounding that's leading to different relationships at the aggregate level than we have at the individual level. So as I said, this notion of confounding is an important one, and it's really next to impossible to completely control for that when you have aggregate data only. If we are in a situation where you have some combination of patient level and aggregate level data, it may be possible to model out that. And that may be something that we'll come to later in the course. There's also a notion that of a different type of bias that's sometimes called aggregation bias or pure specification bias. And that's where we may take a model at the aggregate level, apply at the aggregate level a model that is appropriate at the individual level, and then interpret the effects as individual level effects. And we'll see an example of that, I think, later on when we'll talk about population pharmacokinetic model. You can imagine a one-compartment with oral absorption pharmacokinetic model, where if that may be the appropriate model at the individual level, when you start taking averages and if you're to fit the similar sort of model to the mean data, really because of the averaging of those, the sums of exponentials, you don't end up with something that is itself a sum of exponentials. So that's the notion of aggregation bias, and we see this applied a lot when we're working with logistic regression, because again, the average of the logistic regression model is not the same as the logistic regression model applied kind of on the averages. If you're interested in really delving more into ecological bias and descriptions of ecological bias, I'd really be happy to point you to the paper by John Wakefield in the Review of Public Health. He gives an excellent description of really the whole field and some of the causes and gives some nice examples. So coming back to our meta-regression and thinking about how to do it, let's look at our atorvastatin data that we had, that we've used in the last 2 sessions. And what I've plotted here in these 2 panels, on the y-axis in both panels is the difference from placebo, so that's our treatment effect. And on the x-axis in the left panel is the baseline LDL. It gives us some measure of how severe the patients are in terms of their LDL values. And on the right panel, even though I've mislabeled the x-axis here, this x-axis is really the difference from placebo. So it's giving us a measure of how much did the placebo group respond in that study. So left panel is baseline LDL, right panel is difference from placebo. Is the placebo response. And if we were simply to look at these, one other thing I'll point out is that the different circles, bigger circles represent bigger studies, smaller circles represent smaller studies. So one thing to look at is there a relationship between the difference from placebo, this is our outcome, versus a potential covariate of baseline LDL, or a potential covariate of placebo response. And it probably, I don't know, to my eye, it looks like maybe there's not much of a relationship with baseline LDL, and there may be a little bit of a relationship here with placebo response, probably largely driven by this one large study down here in the lower right-hand corner of the panel. If that wasn't there, you'd probably say there really wasn't any effect. But if we're going to pick one, we'd probably want to pick the placebo response as a potential covariate. So if we were to do that, then our fixed effects meta-regression model would look something like this. It would be that the difference from placebo in the ith study, that's theta hat I, is equal to beta 1 plus beta 2 times the change from baseline in the placebo group in the ith study, plus our residual epsilon I. So I've changed my notation here slightly, but beta 2 now is the effect of the average placebo effect change from baseline moving by 1%. The corresponding random effects model, again, is very similar, but now we've added in our random effect eta I to allow for any additional between study variability that isn't explained by the placebo effect. Okay, and if we were to fit that, we can continue to use the RMA function. The one thing that is now different is that we would be adding in this mods option, and in the mods option we'd be putting in the covariate values into that, the covariate values that we were interested in exploring. And here I've shown you how to use one covariate, and it's a fairly simple extension to add in multiple covariates. So the syntax again is we define yi as our outcome. In this case it was diff. We define either the standard error or the variance of that outcome. In this case I'm using the standard error, and that was called SE diff in our data set. We identify the data, we identify the mods or the effect modifiers. In this case I was asking for the restricted maximum likelihood estimation, and remember I used the SLAB option to simply label the trials when I plot this object. So if we were to look at the output, we'll start here at the top. The estimate of tau squared is now down to around 6.7. Before it was around, I think, 7.3, so we've reduced it a little bit, but not really substantially. We have two tests now. If you remember before, we would simply get this QE, which was the test for heterogeneity. That was equivalent to the Cochrane's Q test. Now we also get something that RMA is labeling as QM, which is a test for whether or not the effects of the covariates are statistically significant. And in this case, we get a p-value of 0.1, which if we were testing this at the 5% level, we'd say is not statistically significant. Just one word about testing for covariate effects in meta-regression. It's oftentimes difficult, unless there's large effects of covariates, to find statistically significant effects. That's in part because the variability in the study level means is typically rather small, and the power to find significant effects of covariates is related both to the residual variance as well as to the variability in the covariates. When you have a small amount of variability in your covariate values, it decreases your ability to detect those significant relationships. In other words, you have less power. So regardless of that, if we are still estimating the effect, what we estimate the effect of the change from baseline in the placebo group as around about minus 0.8. So for every 1% increase in the change from baseline LDL, we have about a 0.8 decline in the mean difference from placebo. With at an effect of 0, no change from baseline in placebo group, we're estimating the effect of atorvastatin to be about 37 point difference. One nice thing that's built into the metaphor package is the ability to plot the metaregression output. And so if we were to simply make a call to the forest function and plug in this output, the model from the metaregression, what it'll provide for us is, in addition to the observed data, which we've seen before as these squares and the corresponding confidence interval whiskers, it also adds in these gray diamonds here, which are the individual predictions at the particular covariate values. So for example, this gray diamond here is centered at the estimated value for a placebo effect of 7.6. And the bottom gray diamond here is plotted at an estimated value for a placebo effect of minus 0.36. So we can see visually here the effect of the covariates, and it's somewhat modest. And what I've added here to the plot, which we need to add in manually, is what the random effects estimator was when we put in no covariate. And so we can see, if we were to visualize a vertical line here coming up out of the middle part of that diamond, there's some heterogeneity being explained by the covariate, but as we see from our statistical modeling, the output from the RMA function, there's still some additional variability that's not explained by the change from baseline in the placebo group. So just when we're working with traditional metaregression, typically there's lots of caveats that are thrown in if you look at the literature on metaregression. And really it's for two reasons. One is oftentimes metaregressions are not pre-specified, and so if they're not pre-specified, frequently those inferences based on those are viewed somewhat skeptically. And as well, even if it is pre-specified, it may be that lots of covariates were looked at, and that even if lots of covariates were looked at and none were found to be significant, there's this notion of sort of limited power in order to detect relationships. So in the traditional meta-analysis world, you'll find metaregressions are certainly performed, but sometimes they're kind of viewed a little sideways, for better or for worse. When we get into our model-based meta-analyses, really our goal there is to some extent, we already have specified the types of models that we're going to be fitting, and whether we're focusing on longitudinal data, we'll be fitting longitudinal models, or landmark data, we may be, in some sense, pre-specifying dose-response kinds of models. Not entirely, but we already kind of have a notion of the direction that we're moving in. So again, some of these caveats are perhaps not as relevant in the model-based analysis world. So I will assign a formal homework for metaregression, but the basic idea is going to be we'll come back to revisit the LDL example using the 80 milligram versus 80 milligram atorvastatin data versus placebo, to look to see if there are any covariates that help to explain the heterogeneity of effect there. Both doing that in the metaphor package as well as fitting those models in WinBUGS. So I think that's a good place to pause and see if there are any questions. So feel free to, if you have any, to give a quick shout on the question board. So I have one question here. The question is there an issue with difference from placebo as a covariate since it's a function of the response? I may not have been clear, but I think the question is a good one. So in here, the outcome was difference from placebo, and the covariate that we looked at was the placebo effect, or the change from baseline in the placebo group. So if we think about the question being, is there an issue with using the change from baseline in the placebo group as a measure, as a covariate on the difference from placebo? That's a good question. I think you may expect there to be some correlation, in the sense that if the placebo effect is large, you may expect to see a smaller difference from placebo. In this case, what we're seeing is that when the placebo effect is large, we end up with a larger difference from placebo. It may be a little bit counterintuitive. And I don't know enough about this particular disease area to say whether that makes sense or not. I think that's a good question. I think in this case, in this particular setting, if we're viewing the placebo effect as a sort of descriptor of something about that population in that study and how it's responding to the drug or to the placebo overall, it seems like an okay covariate to use. But that thinking about whether or not the covariates are appropriate is certainly a good exercise to do before we do any sort of meta-regression, whether it's a fully model-based approach or a more traditional approach. I'll wait for a minute to see if anyone else has any other questions. Okay, well, we'll go ahead and move ahead here. The next small set of topics is a set of miscellaneous topics, and there's really three. We'll talk about a little bit about selection bias and ways for detecting selection bias. Talk briefly about missing data and potential biases that may be introduced in the analysis due to missing data. And again, we'll talk briefly about combining different types of summary statistics, somewhat more in the context of a traditional meta-analysis, and I think we'll revisit this when we come back to talking about model-based meta-analyses. So the issue of selection bias is really comes in when we're not very particularly careful about how we select studies for inclusion in our meta-analysis. And that the bias the notion of selection bias is that we're not really getting all of the studies that were sort of meet the inclusion criteria that we set out with at the beginning of our analysis in the planning stage. And in fact, what we're getting is a selected subset of those that maybe all show efficacy, and the studies that were not that did not show positive effect of the drugs of interest were not published, so therefore we didn't get them in our analysis. That sort of bias, which is called publication bias, or sometimes called the file drawer effect, because those unsuccessful studies kind of get stashed away in the file drawer and never shown the light of day. That can introduce some selection bias, and that's probably the one that's the hardest to detect historically, particularly when we're working with older studies. When we're working with studies that have been published more recently, it's a little bit easier to try to ascertain whether or not there is that publication bias, because of the most drug companies who are conducting these studies, and really any clinical trial drug effects needs typically goes into a registry, and so we can look at those registries of clinical trials and compare those against the ones that have been published, and to make sure that we're collecting all of the ones that were run, or actually including those in the analysis. Sometimes that's difficult because there's a bit of a lag between the time that the study begins and the time that it finishes, and then when the results are published. But at least going forward and into the future, that'll be a good way for us to try to do our best to ascertain whether there is that sort of file drawer effect. The second kind of bias, though, that is harder to control for and harder to really tease out is when we're including studies, but those studies themselves have reported biased estimates of treatment effects. So you might imagine an example of that may be that an investigator only publishes results from a subset of patients that gave particularly favorable outcomes rather than the entire patient population. And or publishes the analysis only of patients that complete the study rather than and so try to, in some sense, kind of ignoring the patients that have discontinued. So if we're presented with those, and in some cases we'll be able to ascertain whether or not that's happened, and in other cases we won't. We won't necessarily know, for example, whether what's being published is a particularly good-looking statistical analysis or way of analyzing the data that presents the data in a good light or not. Again, sometimes we can get at that if we're able to get a full reporting of that particular study. So if, for example, that's a study that goes into the registration of a drug with the Food and Drug Administration in the United States, those typically the FDA will produce some sort of independent summary of the studies, and so you may be able to use those as a reference point to compare to what's published in the literature. In terms of how to ascertain these sorts of bias, we can always, if we suspect there's some biased reporting in a particular study, we can look at running the analysis with and without that study or a collection of studies. So that in that sense, we're doing a sensitivity analysis. That particular issue hasn't really received a whole lot of attention in the meta-analysis literature. What has received much more attention is the notion of publication bias and ways to ascertain publication bias. And the primary tool that's used for that, at least up until maybe the last several years, was something called a funnel plot. And we'll look at how to make those and how to interpret those in the next few slides. If the notion of publication bias is something that's of interest to you and you really want to delve deeper into the topic, I would refer you to this book by Rothstein, Sutton, and Bornstein that was published in 2005. It's a whole book on publication bias and meta-analysis. So what the funnel plot does is it plots on the x-axis a measure of treatment effect, and on the y-axis it plots a measure of information or study size. And typically it's plotted so that a lot of information or a large study size is at the top, and a small information or small measures of study size are at the bottom. So in these two figures I have here on the right of the slide, it's showing the log odds ratio on the x-axis, that's the measure of treatment effect, and the standard error of the log odds ratio on the y-axis. So small standard error corresponds to a lot of information, and larger standard error corresponds to less information. So the idea with a funnel plot is that in the absence of bias, we should get a scattering that kind of looks like a funnel or a triangle, with the center in the largest studies being closest to the overall average effect, and some scattering out to both sides of that, to the positive side and to the negative side, as the studies get smaller and smaller or have less and less information. And so that's just the notion that small studies should have more variability around this overall mean than large studies should. And this can be a particularly useful plot to make. One type of selection bias, though, is when, for example, small studies that show no benefit, in this particular plot they're shown here as the open circles, if those aren't reported in the literature, and we were to make a funnel plot, we might get a plot that looks like the bottom figure here. And so these plots, these asymmetrical funnel plots, are sometimes evidence that there is some sort of publication bias that's going on. Or more generally, as we'll see in a little bit, some sort of small study effects that are differential reporting of small studies. So this is a great plot if we have a lot of studies that are going into our meta-analysis. But it's the funnel plots really suffer from, while they're useful, they do have some drawbacks. So it's certainly the case that if there is bias, then the funnel plot should be asymmetrical. But it's not necessarily the case that an asymmetrical funnel plot means that there is bias, or more specifically that there is publication bias. Other sources, other reasons for asymmetrical funnel plots could be that there's heterogeneity in results. So for example, if we were to make a plot like the one on the bottom here, it may well be that these small studies down here in the lower left part of the plot were small investigator-led studies in different patient populations than the larger studies up here that kind of form this funnel-like shape in the top of the plot. And so it may be that actually the effect in this particular set of patient populations is in fact larger than in the primary patient population where the larger studies were run. And so in that case, we're combining sets of studies and treatment effects that perhaps are heterogeneous, and therefore our funnel looks asymmetrical, not due to any publication bias, but simply due to the heterogeneity in the results that we're analyzing. It may be that the small studies have a poor methodological design or analysis that may be leading to bias. So again, it may be that these smaller studies were reporting selectively their results or reporting the results differently than the larger studies. And the last option is it may just simply be due to a random chance. And when we have a lot of studies, that deviation from the symmetry being due to random chance is smaller. But when we start getting fewer and fewer studies, really identifying the symmetry in the funnel plots becomes more difficult, and it becomes more likely that any deviation is due to random chance. So the recommendation by Rothstein and colleagues is really just to view funnel plots as kind of a generic means of examining small study effects, rather than trying to diagnose specific types of bias, such as publication bias. I think before we do that, before we talk about ways to make the funnel plot and kinds of scales to plot them on, let's look at the funnel plots for the two examples that we've been working with. So here on the left is the funnel plot for the atorvastatin 10 milligram versus placebo studies. This is a plot that comes out of the metaphor package using the function funnel. And just to make these plots, you can fit a model using the RMA function, and then if you simply use that model object as an argument to the funnel function, you'll get out the funnel plot. With these few studies, I don't know, I'll leave it to you to ascertain whether you think there may be some small study effects here for the atorvastatin study. In the right panel, we have the pancreatic cancer 6-month mortality study comparing gemcitabine plus chemotherapy to gemcitabine alone. And again, I'll leave it to you to ascertain whether or not there's any sort of small study effects going on here. I'll let you think about that a little bit, and maybe we'll take a poll and see who thinks there's publication or small study effects going on with the either or both of those analyses. So I would say, it's difficult to really say with such few studies, but it seems to my eye that perhaps there's a bit more evidence in the pancreatic cancer analysis than there is in the atorvastatin analysis. But it's, again, with these small number of studies, it's a little bit hard to say. So there are some guidelines for making funnel plots. And I'll go back here to full screen. That give us some guidelines around what to plot on the x-axis and what to plot on the y-axis. As you can imagine, there's lots of different measures of treatment effect. Typically what we'll want to do is make the measure of treatment effect the same as the one that we're performing the analysis using. And generally when we're working with binary outcomes, you'll see in the literature most of the recommendations are to work with the log odds ratio. So in that case, the measure of treatment effect would be the log odds ratio, and the measure of study size or measure of information would be the standard error of the log odds ratio. Similarly, if we're working with numerical or continuous outcomes, we might work with the treatment difference as our measure of treatment effect, and the standard error of that treatment difference, or the sample size as a measure of information in that study. I think that's all I'll say about that. Again, as I said before, if you're interested in really diving into this notion of publication bias, the book by Rothstein and colleagues is very good. The book that I referenced at the beginning of the course by Ann Whitehead also has a chapter on publication bias. So if you have that book, that might be a good place to start. In both of those, particularly in the Rothstein book, they developed some methods for formally testing for selection and publication bias and ways to attempt to correct for it. But I'll leave it to you to follow up on those references if you're interested. Another sort of plot that's useful in this context is something called the Radial Plot or the Galbraith plot. This is a plot that I'm glad I don't ever have to make by hand, because it's I wouldn't even really begin to know how to make it. But fortunately, there are tools for us in the Metaphor package that do that. And this really kind of, in some sense, has three axes. We have, it's a plot of the standardized treatment effect versus a measure of precision. Parts of those elements are similar to what we had in the funnel plot, but there's kind of a third axis, a circular axis that we'll see in a second. That's the treatment effect axis. And this, when we fit a regression line through the data points, forcing it to go through the origin, that in that particular plot it ends up pointing to the overall estimate. In some sense, this is useful for assessing consistency of effect across studies. So here are some examples of radial plots. Again, we can get these out of the Metaphor package using the radial function applied to a fitted object. In this case, what the default scale is for the x-axis is 1 over the variance of the outcome. That's our measure of precision, and what's plotted here on this axis is on the vertical axis is the standardized effect. So that's the difference here, yi divided by the standard error. And then out here is this circular axis that points us to the treatment effect. And the way that you would interpret that, it's a little bit complex, is you would draw a line from 0 here through the data point out to this axis down here, and that would give you the measure of the treatment effect, which is the yi for that observation. So really what's being plotted here is standardized treatment effect versus the measure of 1 over the standard error. And because of that, if we draw this line out, we get this circular axis out here. Also because of that, if we fit this regression line through the data points, forcing it to go through the 0, 0 point, we get and extend that line out to this circular axis is where we intersect and get the overall treatment effect. And you can imagine putting a confidence interval as the package does here for us. Okay. I think I'll pause there for a second. I saw that there was another question here, so let's address that. The question is, would single-arm studies be considered as a source of the first type of bias, i.e. biased estimates of treatment effects? I need to think about that for a minute. Would single-arm studies be considered as a source of biased estimates of treatment effect? I'm not really sure how to answer that. There certainly is, and if you'd like to follow up with a clarification, feel free. There's certainly, working with single-arm studies in and of themselves present some logistical difficulties, or not logistical difficulties, but difficulties in interpretation of the modeling results. In the sense that if we're trying to make comparisons between, say, two treatments, and the majority of the data coming from to make that comparison are coming from single-arm studies of one treatment versus single-arm studies of a different treatment, we need to make sure that we're being able to control appropriately for other effects that may be leading to differences in outcomes. So, for example, if we're working with in an oncology setting, and we have single-arm trials where we're measuring something like a response rate or progression-free survival, there can be differences due to patient populations that were enrolled in those studies that can influence to a large degree response rates or progression-free survival that may be larger than differences between drugs. And so if one drug was run in let's say a patient population that's relatively healthy relative to another patient population, and we haven't adequately controlled for that in the model, then we could be overestimating the differences between the two treatments. In that sense, you could think about it as bias. I think you may also think about it in some ways as a kind of a missing data problem, in the sense that we just are, if we wanted to make those comparisons, we're kind of missing the comparator in the study that might allow us to connect the two studies more directly. And we'll kind of come back to that notion about comparability and connecting studies when we get into the topic of network meta-analysis. So I hope that addressed your question, and if it didn't, please feel free to follow up. Good question. So there was another question here. What is the shaded area in a radial plot? Let's go back and look at that. So the shaded region on these radial plots is a 95% confidence band. And the idea, it's a confidence band here on the standardized scale. And the idea is that once we've adjusted for, once we've standardized relative to the standard error, we've kind of removed the fact that smaller studies have bigger standard errors, so and more variability. So the confidence band here, we should expect to see, in this case, 95% of those points falling within that shaded band. And if we were to see more studies or lots of studies falling outside that band, that gives us some idea that there's some inconsistency amongst the studies, and that perhaps we need to account for that in our modeling. Looking at these two plots, it's hard to say. I would say there's not a strong evidence of any inconsistency here. Each of these has one point that's falling outside of that gray band. Okay, so let's think a little bit about our second topic, which was missing data in meta-analysis. We can think about missing data as coming in probably in lots of different ways, but let's think about two specific ways. One is that notion that an entire study is missing, and that's what we've already talked about as publication bias or the file drawer effect. It may also just be coming up because we have done an incomplete search of the literature, so the study may be published, but we just haven't captured it in whatever literature search that we've done. The second type of missing data is every clinical trial, nearly every clinical trial has some sort of missing data, and that when missing data within an individual study can lead us to some potential problems, and we need to just at least think about what they may be when we're doing our meta-analysis. So here's an example from a paper by White, Higgins, and Wood that's comparing an experimental treatment with a control treatment across 6 different studies. And what they've tabulated here is the number of successes and number of failures on both the experimental arm and the control arm, as well as the number of subjects that were missing. So they weren't able to ascertain success or failure. And here we see that the percent missing is varying from no missing data in the first study to 24% of the data being missing in the fifth study. And so we have varying degrees of missingness, and that can present problems, as well as the fact that, well, we'll talk in a little bit about other potential issues we may have with missing data within a study. And those really come down to, we can if we think about the classification scheme for missing data, we oftentimes think about it as, broadly speaking, whether the missing data is informatively missing or non-informatively missing. Informatively missing being where the probability of a patient or an observation being missing being related to the value that we don't get to see. And clearly in that setting, if we're having that within an individual trial, there's informative missingness, then the estimates of the treatment effect that are being reported in that study are very likely to be biased treatment effects. And whether that's based on the observed means or a summary that we're pulling out of, let's say, a statistical analysis that we're putting into our meta-analysis. Those are likely to be biased, particularly if we're just working with the raw mean data. What's interesting, though, is that even if there's non-informative missingness, so think about that in the most general case is just patients are randomly dropping out over the course of the study, has nothing to do with their outcome of interest. Even in that setting, we can still get biased estimates of treatment effects if the missingness depends on kind of the true study level effect. So it may be that within a study there's missingness, but if you imagine that we have kind of in this random effect setup, we have the true study effect for study 1 is a very large effect. And in that particular study, the missingness is completely at random, but it's perhaps larger than it is in a different study where the true treatment effect for that study is small and the missingness is less. So if we have this correlation between the true treatment effect in that random effects model sense and the missingness probability, we can get biased estimates of even if there's no bias within each of those studies individually. And I think this becomes really it's a problem even in traditional meta-analysis. The problem is probably compounded somewhat when we get to working with longitudinal data. It's probably really an area for additional research. There hasn't, to my knowledge, been much work done in longitudinal, particularly in the model-based setting, and longitudinal model-based meta-analysis of longitudinal data and the impact of missing data. So there are ways to try to evaluate and ascertain the sensitivity to missing data. As we talked about before, if we're looking to ascertain something about publication or small study bias, we can use funnel plots, perhaps radial plots. But by and large, the issue is typically ignored in meta-analysis. That is, missing data within individual studies is ignored. There have been a small number of attempts to try to address that. In particular, there's a pair of papers by White, Higgins, and Wood that try to do a sensitivity analysis to missing data mechanisms. So they look at a sensitivity analysis kind of going from a non-informative to informative missingness. And a paper by Wan and Little in 2009 attempts to give some statistically principled approaches for handling bias when the dropout is related to that underlying size of the treatment effect. So this notion that if the dropout or the missingness within a study is completely at random, but across studies there's some correlation between missingness and treatment effect, they developed some approaches to handling that. But as far as I know, that's sort of the extent of the meta-analysis literature in terms of dealing with missing data. So it's really an area open for additional research. So the last little topic we'll talk about briefly here is how do we combine trials that report different summary statistics? So you can imagine that you may, if you're working with survival data, you may have studies that report a hazard ratio and others that might report something like the % of subjects that survive out to 1 year. You may be able to extract that from a Kaplan-Meier plot, or that may just be tabulated. There may not even be Kaplan-Meier plots reported. If you're working with binary data, it may be that some studies report a responder rate. So if you're thinking, let's say you're working in a disease area for treating depression, and you're working with the Hamilton Depression Rating Scale, some studies may report a % of responders based on change from baseline Hamilton Depression Scale, and other studies might report the absolute change from baseline and a standard deviation. So we have some studies reporting that binary outcome and some studies reporting a continuous outcome. And then the third example might be that some studies report a mean change from baseline and others might report a median change from baseline. It may be that they, a different sort of difference in summary statistics, maybe that some trials report they may all report a log odds ratio, but they may be reporting them based on just simply on the raw data or on some model that's tried to adjust for stratification factors or covariates. And so, how do we work on pooling those kinds of data? That's actually a harder question to deal with than the first one. And then, the last kind of issue we deal with frequently is we may be measuring in a disease area where lots of different scales are used across studies. So it may be in Alzheimer's disease, for example. Some studies might report ADAS-Cog, others might report CDR, others or MMSE. Or if you're working with a quality of life scale, there are lots of different quality of life scales. If you're working in, I don't know, other disease areas, you can imagine that there are different scales, particularly if it's in a disease area where the scales haven't been standardized. This becomes can be a difficult issue to tackle. So there are ways that we can try to handle this, but typically they're all going to involve making some sort of assumption, typically some kind of untestable assumption. And those assumptions can, to a large extent, affect the validity and interpretability of the results. So depending on how you're planning to use this analysis, how much you want to rely on those assumptions, or may depend on how much you want to rely on those assumptions. I think if we're doing this analysis to help us kind of make a reasonably informed quantitative decision about a drug development program, making lots of assumptions like along the lines of trying to pool disparate types of data may be more tenable than if you're trying to convince a payer about how to pay for your drug or to put it on their registry. So it's a sort of idea about pooling different endpoints is probably depends on where you are and how you're using your meta-analysis. But let's talk a little bit about how to do it. So if we have these different outcome scales or different instruments, so think about the ADAS-Cog versus the MMSE, how do we pool those? Typically what's done is we'll use some sort of standardized response or standardized difference. So it may be that you take if we're working on difference from placebo for both of those, you may take the difference from placebo for the ADAS-Cog measurements divided by their standard errors. And for the MMSE, you would do the same thing. You take the difference from placebo divided by standard error, and you work with that standardized difference. And the assumption there is that that one standard error unit on the ADAS-Cog scale is equivalent to one standard error unit on the MMSE scale. And depending on the scale and where you are in those scales, that may or may not be a reasonably good assumption. But that's typically the way that's handled. Some way of translating, and typically it's through that standardized difference. If we have different summary statistics, and we'll talk about those in the next slide, typically what's done is to try and convert those to some common measure or some measure that we can, some scale that we can work with those on directly. And depending on how we're doing that, and we'll see those slides, see that in the next slide, the assumptions there may be completely untestable. You know, and lastly, if you can ever get your hands on the patient level data, that's the best thing to do, because then you can derive any of the endpoints that you are working with. So if you have some studies in the literature reporting responder rates, and you have patient level data for an internal compound at a pharmaceutical company, you can, of course, derive those responder rates, and that would be sufficient in this traditional setting. Of course, if you're working with data that's outside of your particular company or your particular research institution, that's typically difficult to do. So I'll give you two examples of how we might combine different endpoints. The first is if we have hazard ratios reported in some studies and percent surviving reported in other studies, we can, if we conceptualize the treating the percent surviving as being interval censored, then it turns out that the odds ratio of those percent surviving approximates the hazard ratio. And this is actually something that's used fairly frequently in statistical analysis in combining data. And the assumptions that are being made here are about the censoring mechanism, the sort of interval censored nature, and that over that interval the censoring is happening at a constant rate. Another type of different endpoints that need to be combined that happens fairly frequently is when some studies are reporting responder rates, as in the Hamilton Depression Scales example, and other studies are reporting, let's say, a mean change from baseline. In that case, what you might want to do is think about translating those mean change from baselines to some sort of responder rate scale. And one way to do that would be to assume that the responder rates, would be to assume that the change from baselines in that particular study follow a normal distribution or some other distribution, a parametric distribution. And given a mean and a standard deviation, you may be able to derive the percent of subjects that fall in the tail of the distribution that correspond to being a responder. I can't remember, but I think something like if you're working with remission rates using the HAM-D, I think one definition is a HAM-D score that's less than 10. So if we knew something about the HAM-D scores at a particular time point in the standard deviation, if we were to make some assumptions about the distributional shape of those, we could try to impute what the percent of patients are in that study at that time point who have a HAM-D score less than 10. So those are two examples of combining different endpoints, and I think we'll talk about more later on. In fact, I have two more here I forgot about. So if we're combining means and medians, sometimes we may just go ahead and ignore the fact that there's a difference. And that's making an assumption that our distributional shape is symmetric. If we have a standard error, and you may imagine that we can get a standard error reported for a mean, but they may not report any sort of measure of uncertainty for the median. Depending, if we again assume this a normal distribution, when in fact you can derive this through simulation for other distributions, you can kind of impute what a standard error may be based on that. So it turns out that with a normal distribution, the standard error of the median is about 25% higher than the standard error of the mean. And lastly, if we have ordinal data, and some studies are only reporting certain categories of that, and other studies are reporting other categories. So the example that comes to mind here is when we're in psoriasis, working with the PASI score, or PASI responder rates. You see an analogous sort of thing in rheumatoid arthritis when working with ACR scores. So in both of these, you have, in the PASI, you might have a what are called PASI 50, PASI 75, and PASI 90 that correspond to 50%, 75%, and 90% improvement from baseline. With ACR, you might see ACR 20, ACR 50, and ACR 70. So those are 20, 50, and 70% improvements in those scales. And some studies might report only PASI 50, and others might report PASI 50 and PASI 90, and others yet might report PASI 50 and PASI 75. And there are fairly simple ways of combining those data, treating them as ordered categorical data, because of the somewhat hierarchical nature of those. If you know that somebody's a PASI 75 responder, just by definition, they're also a PASI 50 responder. So in that kind of case, then combining those different endpoints is actually fairly straightforward and makes relatively few assumptions. So this is the point in the course where I was originally planning to talk about network meta-analysis. I think that the more I thought about it, it seemed like it would make sense to talk about network meta-analysis after we've had some introduction to model-based meta-analysis, because really network meta-analysis is something of an extension to traditional pairwise meta-analysis that tries to get at making comparisons between treatments using both direct data, so head-to-head data from individual trials, as well as indirect information. So if we have placebo-controlled trials for drug A and placebo-controlled trials for drug B, the network meta-analysis allows us, still within this traditional meta-analysis framework, to make inferences about the differences between treatments A and B, even if they've never been studied head-to-head. And if they have, it's a way of pooling data that pools information on both the head-to-head comparisons as well as the indirect comparisons. Sometimes you'll see these referred to as mixed treatment comparisons meta-analysis or multiple treatment meta-analysis. And I think what we'll do is we'll come back to this later in the course. We'll probably have a whole lecture on this, including code for fitting these models. So that's really where we're coming to an end for the traditional meta-analysis section for now. We'll pause there and see if there are any questions, and then we may take a short break before Bill starts in with the model-based meta-analysis section. Okay, I don't see any questions. Bill, do you want to? How long of a break do you want to take, or do you want to just go straight into your to the?
Oh, let's go ahead and take a short break here and come back at 3:20.
Okay, sounds good. So we'll come back in about 5 minutes.
Right. Okay, looks like we can go ahead and get started again. Jonathan, are you still on the line?
I am, yep.
Yeah, I just had a question for you. Were you planning on assigning anything that you'd be going over on Monday?
I will, yeah. I'll assign that. I'll post it to the training site on probably tomorrow morning.
Okay, good enough. Just wanted to make sure we weren't missing something.
Oh, yeah, thanks for clarifying.
Okay, let's go ahead then, and we'll take a sort of an initial start in discussing model-based meta-analysis to close out today. Let's see. Hopefully, the audio or the slides should be visible. Okay, so what is it? Well, first of all, some things Jonathan's already touched on is the difference between what we've been terming traditional meta-analysis and model-based meta-analysis is not a sharp one. We're really kind of talking about matter of degree or sort of an accumulation of different features of the models we're working with. As I say here, it's kind of a continuum going from the traditional meta-analysis to meta-regression to model-based meta-analysis. In fact, one could easily call model-based meta-analysis really just a category of meta-regression. But for our purposes, we'll just use that term here. I'll either say model-based meta-analysis or MBMA. I'll use that to refer to meta-regression using models based upon some pharmacometric knowledge and principles. And these will often employ models that describe some efficacy or safety related response as more often than not a nonlinear function of drug exposure and possibly time. And they may also consider other covariates such as demographics and other baseline measurements. So what is the role? And I guess what I see as the role of MBMA is as distinguished from some of the methods that you've already been hearing about, is it's a tool for dealing with objectives that aren't adequately addressed, by traditional meta-analysis. This may be some indirect statistical comparisons, in other words, comparisons of treatments that were never administered within the same study. And Jonathan's already mentioned a somewhat more, what I term here, a statistical approach known as network meta-analysis. It's a tool that we can use for predictions and inferences about responses that would occur at values of independent variables that were never directly studied. For example, you may want to use a model to make inferences about what the response to a dose is that was never actually administered. So it may be either an interpolative or an extrapolative sort of exercise. And we can sometimes use models to integrate what I just refer to as here as heterogeneous data and knowledge. For instance, if you go back to the first lecture where I gave a very brief installation of or brief presentation of an example where preclinical data and clinical data for various compounds was combined within a framework of a single model-based meta-analysis. Certainly, a conventional meta-analysis would be inadequate to deal with that kind of a problem. The next thing I want to talk about are some of the tools we're going to be using as part of this. And the kind of tool that I'm going to be using for the subsequent examples. We'll be using WinBUGS for the remaining examples, and that raises a couple of questions. It raises the question of, well, why use a tool that's primarily intended for Bayesian analysis? In other words, why Bayesian? And then otherwise, why WinBUGS? So I just wanted to touch on that here. Well, why Bayesian? Well, part of this is it's just kind of a natural extension of the sort of hierarchical models we commonly use in population modeling, where we're basically layering on another layer of randomness in here that describes uncertainty as part of the modeling. So it's just another layer in the hierarchy. Model parameter estimates and model-based inferences can be done using what is essentially a single-step analysis process, where you get the posterior distributions right out of that distribution, and your inferences are based on those posterior distributions, versus doing it as more of a two-step process where the first step is basically getting point estimates for either your for either model parameters or model predictions, and then in a second step try to characterize the uncertainty in those point estimates. One consequence of this too is I find that the inferences have a more natural and direct interpretation than those from a frequentist perspective. But those three are kind of sort of soft arguments, I would say, for why Bayesian. The really strong reason for considering a Bayesian analysis would be that prior information about model parameters is easily integrated into the modeling process, and that provides you with another strategy by which you can combine information. So not only are you able to combine data in the context of a meta-analysis, but you're also able to combine other quantitative information into the analysis if you wish. And that's really where where Bayesian methods are, where they really offer a great deal of an advantage. Now, having said that, for most of the examples that we're going to be doing within the course, we're not going to exercise that to a large extent. We do towards some of the later examples we do, but up to then we tend to we'll be using relatively uninformative prior distributions. And if you had a frequentist or a maximum likelihood tool that was sufficiently flexible to implement the models, they would actually be perfectly acceptable for most of those. And that leads me to the other reason why we're going to be using BUGS tools within the context of this course, and that's flexibility. And particularly the BUGS model specification language is very flexible with respect to the stochastic structure of the model. Let's see, I just got a comment here. What is it? Let's see, somebody's saying that the slides are not advancing here. Let's see, that came from you, Mike. I'm looking at the moment at slide 148, so I guess maybe I'll ask for input from folks. Are they seeing slide 148?
Bill, I'm seeing slide 144.
Okay, that's interesting. Let me see, it says... So we got audio, obviously. Trying to think of any buttons I can push on here that would be of any use. Now let me actually stop the presentation of this thing and try and re-show it and see what happens. Okay, let's see if things change there. Anything, Jonathan?
No, it's still the same.
Let's see. I think of what I can do short of interrupting the entire thing, which will put a hitch in our recording and everything.
If we just, how about if I'll just make myself the presenter real quick, and then I'll make you the presenter, right?
Okay, see what happens.
I think you may have to pull it back.
Okay. Okay.
There we go.
You seeing something? 148.
Yep, and I can see your mouse moving too.
Okay, so we'll go ahead. Let me go ahead and change it here. So what we were looking for, what we saw before was the Y Bayesian, and I pretty much read what it said on the screen. So we probably don't need to repeat that. So back to slide 148. Okay, so one of the primary reasons why we're using BUGS for some of the model-based meta-analysis work here is really its flexibility. The BUGS model specification language is quite flexible, at least with respect to the stochastic components of the model. So for example, you can put as many levels of variability in the model as you like. In some contexts, it's useful because you can actually combine several submodels that have very different stochastic structures and fit them all simultaneously. That's something that's difficult with most of the other model tools that are commonly used in pharmacometrics. And another one is there's a large selection of built-in probability distributions that are within the BUGS model language, which gives us again another significant source of a flexibility here, and these are, particularly the different, the being able to have more than, say, 2 levels of variability, and having access to a variety of probability distributions are something that we'll be exercising in some of the examples here. So as we go along through some of the examples we'll illustrate, some you'll find are fairly easy to implement in tools like non-mem, for example, or maybe using NLME within R. Others will be ones that are not readily implemented with such tools, and that's where BUGS shows some advantages. Now, having said that, BUGS is not as flexible with respect to models where the deterministic parts of the model are complex. And that's a consequence of the fact that uh, BUGS does not have any nice built-in control structures like if, then, else, and how did it end up being true loops? That's supposed to be like do loops. Anyway, so or for loops actually. It does, or I'm sorry, I do know what I meant by true loops. True loops in the sense that it actually describes a sequence of actions. The loops within BUGS actually means something a bit different than that. So the fact that those aren't there makes it sometimes more difficult to implement certain types of models. Okay, having said that, it turns out that you can write custom functions for WinBUGS when necessary, albeit it's a fairly clumsy operation to do so, but that does give you access to some of that complexity when it's really needed. So the point being here is we're using BUGS here mainly because of that flexibility in the stochastic structure, and that lets us easily do things like incorporate, 3 and more levels of variability and use distributions that are just not readily implemented in other tools. So let's sort of talk about the process here, and this will ultimately lead to our first illustration of doing a relatively simple model using BUGS to do a meta-analysis. And let's talk about modeling. There's different types of sample statistics one might model, but let's start out with dealing with sample means. So one of the first things we have to figure out in our model is what sort of a sampling distribution are we going to use to describe it. And you can say, as I lead in here, I talk in terms of choosing a sampling distribution and adjusting for sample size. So again, let's start with our sort of the simplest case where we've got one sample mean per treatment arm. The primary independent variables in this will usually describe the treatments. For example, what drug and what dose of that drug are being administered within that treatment arm. And frequently we find that the distribution of the residual variation in our sample means can be adequately described by a normal distribution where we adjust the variance for the sample size. And that's what we're showing in this equation. So here we're imagining y bar here is some observed sample mean. And in our model, we're going to describe that as being normally distributed with some underlying mean mu here, and the variance here is the variance in the mean. So when I say sigma squared over n, you can conceptualize this sigma squared as being the variance of individual observations, so that sigma squared over n would then be essentially a model-based standard error, actually the standard error squared, or the, if you like, the variance of the mean, rather than the variance of the individual values. A possible justification for using this particular sampling distribution would be that, well, if that's what would happen if the underlying individual data was normally distributed, this is how the mean would be distributed in those cases. In some cases, an argument is made that a mean may be appropriate because according to the central limit theorem, the mean would be asymptotically normal. So both arguments sort of lead you to essentially the same place. So that's what we'll commonly use for our sampling distribution. In our model-based meta-analysis, this mu will usually be some function of things like the treatment, function of dose, a function of time, possibly a function that may also be adjusted for different drugs, for example, as well as incorporating other covariates. And we can use other approaches to this where we use the sort of same basic idea, but instead of using a model-based, a model estimated value for our variance, we might instead choose to use the observed standard errors in the means within here. So that's what we're showing here, is you could go ahead and use the reported sample standard error for the mean and square that, and that would serve as your variance estimate here within this. That has the downside of essentially assuming that you know the variance with some accuracy, but it has the potential advantage of allowing for inter-trial and even inter-arm differences in that residual variability. Here I'm just commenting that some alternative distributions for sample means might be considered, things like log normal, or, to deal with maybe something that's always non-negative, or maybe a t-distribution if you want something that's robust to outliers, where that ends up being a little tougher to deal with in terms of adjustments for sample size. So I comment here that rigorous treatment of sample size adjustment and justification based on the distribution of individual data, as I say here, are elusive. And the reason why they're elusive is you don't end up with nice simple arguments like with a normal distribution. If the individual data are normally distributed, then the mean is also normally distributed. That sort of argument doesn't follow for things like a log normal. So the mean of log normally distributed individual data is not log normally distributed. In fact, in the limit, according to the central limit theorem, it would actually be normally distributed rather than log normally. So I just comment here that if you log transform your sample means, it's not clear what the appropriate sample size adjustment for the variance would be in those instances. Another issue that comes up here is, whether you work on the original scale of the measurements, or do you work with things like baseline corrected values, change from baseline or percent change from baseline. And here, I guess I'm kind of indicating that I would, I'm pretty agnostic on that issue depending upon the context you're in. So as I say here, clinical measurements are often reported in terms of change from baseline or percent change from baseline. And if you're modeling endpoint data, and here I'm contrasting that with longitudinal data. So when you're modeling endpoint data, the choice of whether to use the measurement on the original scale or a baseline adjusted scale really depends upon what statistics are available to you and the intended use of the model. As I say here, if baseline corrected value is commonly used for primary statistical analyses of clinical trials for the indication you're looking at, then modeling of that statistic is probably a logical choice and would probably appeal to the relevant decision makers that are likely to be the consumers of the work that you're doing. And I also argue that in some cases, predictions on both the original and baseline adjusted scales may be desired. And in such cases, it may be necessary then to construct models for both if that's the case. And I mentioned that either or both models may include, a mean baseline response as a covariate as part of the modeling exercise. And then I just go on, take a step further here and just mention that with longitudinal data, where a baseline measurement is part of that, the longitudinal sequence of data, a reasonable approach in that case would actually be to model the entire time course on the original scale. But then if you want to make inferences on the baseline corrected scales, you can still do that by calculating the difference between the predicted values for a given time and the predicted value for baseline. So in that case, you can kind of have your cake and eat it too. This is just commenting on incorporating other covariates. So in addition to describing the effects of treatment, we may want to account for differences in results among trials and treatment arms. There may be summary statistics for covariates describing the patients in a treatment, things like mean age, mean weight, fraction of females, and so on. In addition, there may be covariates general to a whole trial, like geographic location, phase of development, and so on. And all of those are potentially fair game, subject to some of the caveats you heard earlier today around problems such as ecological bias when it comes to actually interpreting what the covariates mean in these models. And finally, we will want to quantify unexplained variation among trials via random effects, in other words, inter-trial variation. So we're usually talking here about doing random effect models within the context of model-based meta-analysis. And for our initial example here, where we were talking about having only one observation per treatment arm, inter-arm variation and other sorts of residual variation are not separately estimable. So we're generally only going to be working with, essentially two levels of variation. We're going to have our residual variation, which really is a combination of both inter-arm and residual, and then separately having an inter-trial variation component as part of the modeling. Oh, let's see. I thought we already hit on this. I forgot I had this slide. Let's see. Yeah, this is something Jonathan had already mentioned in the context of meta-regression, but I suppose it doesn't hurt to repeat it. Just a reminder that because your patient-specific covariates are in the form of summary statistics, their values will then tend to cover a narrower range than the individual values would have if you had them available to you. As a consequence of this is that they're less informative about their effects unless the data has been somehow stratified based upon those covariates. So, for instance, if you only get if all you know is what say the relative fraction of males and females are, chances are as you look across trial, that's not going to vary by a great deal from trial to trial, and you're not likely to be able to make very strong inferences about the influence of gender. On the other hand, if you have data that's actually stratified by gender, that might actually be the basis for making more relevant inferences about gender. Unfortunately, that's usually not available to you when you only have aggregate data. Let's see. I'm actually going to, let me actually stop here, see if there are any questions at this point. Okay, I'll keep my eye peeled, see if anything comes up here. But the next place I was going to be going is actually to do a demo illustrating a model-based meta-analysis using WinBUGS. But I'm thinking that that's something I would prefer to hold off until the next session so that you have it in fairly close proximity to the hands-on example that will be that will use some of the methods that we're going to talk about there. So rather than actually jump into presenting that demo, I think what I'll do is, as I say, is I'll hold off. We'll talk about that. I guess that'll be next Wednesday, and follow it up with a homework assignment that'll use pretty much the same techniques that I'll be demoing next Wednesday. So I'll just hang on for another minute or two to see if there are any questions, and if not, we'll be closing out the session for today. Okay, nothing new seems to be coming up on the question board. As you heard from Jonathan, I guess he will be posting something on the course website for some homework that he'll be going over next Monday. So I guess keep your eye peeled for that. I guess other than that, Jonathan will see you on Monday, and I'll look forward to talking to you again next Wednesday. Goodbye for now.